So on Monday, we talked about exact and measured numbers. We talked about significant figures and metric to metric conversions. And so today we're just going to review on some of that stuff. So the first question, we want to know which of the following are exact numbers. So exact numbers are numbers that can be counted, or numbers or conversion factors within the same system of measurement. And so it's not one of those two criteria. It's a measured number. So when we look at the first number, 6.7 times 10 to the 8, we see that the unit is meters. So meters is a measured quantity, so this would be a measured number. Next we have 3.3 times 10 to the negative fourth, and here you see it's centigrams. So again, grams is a measured quantity, so this would be a measured number. Now you see something like 3,500 miles. It may look exact, but again, the quantity that's being measured is miles, so you have to use a measuring device to obtain that value. So this is also a measured number. It just means that it only has two significant figures. Now the next one, we have a conversion factor. We say 16 ounces equals 1 pound. And so here, ounce is in the standard system of measurement, and pound is in the standard system of measurement. And so here we're just going from standard to standard. So this would be an exact conversion factor. Next we have 1 mile equals 1.607 kilometers. So again, mile is the standard system, kilometer is the metric. So here we're going from standard to metric. So this would not be an exact conversion factor because we're going from the standard English system to the metric system. Next we have 45,000 coins. So again, you may say, hey, it's 45,000, but we're measuring, or the value is coins, and so you can actually count the individual coins and know there's exactly 45,000 coins. So F is also an exact number. And then lastly, we have 1 quart equals 946 milliliters. So quart is the standard system, milliliter is the metric system. So we're going from standard to metric. So this is a measured conversion factor. So the only ones that are exact are D and F. And so D is exact because it's a conversion factor between in the same system of measurement. F is exact because you can obtain it from count. Now moving on to number 2. Here we want to know how many significant figures are in each number. So in the first one, we have 204 seconds. Second is a measured quantity, so this is a measured number. And 2 and 4 are non-zero, so they're significant. And this 0 in the middle is significant because it's a captive 0. So this one has 3 significant figures. Next we move on to B. Here the quantity is in feet, and feet is a measured quantity. So when we look at this number, the zeros before the first non-zero number are leading zeros, so they're not significant. The 3, the 7, and the 8 are significant, and also this 0 at the end because it's a number less than 1. So this would have 4 significant figures. Next we have 405,000 kilograms. Again, kilogram is a measured quantity. The 4 and the 5 are significant because they're non-zero. The 0 between the 4 and the 5 is significant because it's a captive 0. And the other zeros are insignificant because there's no decimal point at the end. So those are what we call placeholding or trailing zeros. So this would have 3 significant figures. Next, we have 850 rice kernels. And so here the rice kernels is something you can count. You can count 850 kernels of rice. And since it's something you can count, this is actually an exact number, so it has an infinite number of significant figures. Moving on to E, we have 1.03 times 10 to the 4th liters. Liters is a measured quantity, and since this is in scientific notation, all digits are significant. So this would be 3 significant figures. And finally, we have 3,050 nanoseconds. So nanosecond is a measured quantity. The 3 and the 5 are significant. The 0 between the 3 and the 5 is significant. And this is because it's a captive 0. And the 0 at the end is a trailing 0, but now there's a decimal point at the end. So that 0 is significant as well. So there's 4 significant figures. So in question 3, what we're going to be doing is we're going to be rounding to the number of significant figures in parentheses. So in the first one, we have 3,565, and we want to round to 2 significant figures. 1, 2. To the right of a 5 is a 6. So that means we're going to round the 5 up to 6. So this will be either 3,600 or 3.6 times 10 to the 3rd. Next, we have 100,400, and we want to round it to 2 significant figures. So we go 1, 2. After the 0 is a 0. 0 is less than 5. So we're just going to retain this 0. Now, if we try to write this as a normal number, we write it like this. It's not going to have 2 significant figures. It would have 1. And even if we put a decimal point, well, then we won't have 2 significant figures. We have 6. So the only way you can write this one is in scientific notation. We say 1.0 times 10 to the 4th. Oh, no, 5th, my bad. And that's the only way that this one can be written, because we need 2 significant figures, and it's such a large number that we have to write it in scientific notation. This should be a 10, not 1 times 20. There we go. Now in C, we want to round to 3 significant figures. And again, you don't start at the first 0, you see, because these 3 zeros are significant. And even this one. So we can cross them out. So we start counting 3 significant figures when we get to the 8. So we go 1, 2, 3. After the 4 is an 8, so we're going to round the 4 up to 5. So we get 0.000895, or you can write it in scientific notation. There you go. Now the next one, I need my calculator. Find it. There we go. So the next one, we're given us some operations, and we want to determine what the answer is. We want to round it to the correct number of significant figures. So in A, we have a multiplication of 3 numbers. So when you put it in the calculator, the calculator gives you this. But now we have to round to the correct number of significant figures. So 7.50 has 3 significant figures. Now 5,000, since there's no decimal point at the end, only has one significant figure. And then 0.8540 has 4. So with multiplication and division, your answer should have as many significant figures as the one in the operation with the least number. So here, there's only one significant figure, so our answer should only have one sig figure. So after the 3 is a 2, so we just drop the 2, and you just don't answer. You can't just say 3. We talked about this on Monday, because 3 is not the same as 30. You got to put a 0 there as a placeholding 0. So the answer would be 30. Now in B, we have a addition operation, and with addition, our answer should have as many significant decimal places as the number with the fewest significant decimal places. So if we look at these, each number, the first number has a significant decimal place down to the tenths, second number has it down to the thousandths, and the third number to the 10,000ths. So since the one with the least number of significant decimal places is to the tenths, our answer is going to be rounded to the tenths place. So when we do this operation, the calculator gives you this. Now we have to round to the tenths place. So it would just be 103.7, because after the 7 is a 4. So just one correction, in 4A it should have been 30,000 and not 30. So you can either write it as 30,000 or 3 times 10 to the 4th. Now switching gears just a little bit. Now we want, and this is similar to the discussion question number 2, when we want to record measurements from measuring. And so I have two different types of measurements here. In one, we're measuring the length of a piece of metal, and in the second one, we're measuring the volume of liquid in a measuring device. And so again, from what we talked about on Monday, significant figures is a certain digits plus one uncertain or estimated digit. And so the uncertain digit we get from estimating. So the certain digits are based on the smallest tick mark on the measuring device. So when we look at our ruler, let me move this right there. So one thing with measuring, the rules that we use for the metric system, for rounding or for determining the estimated digit, are going to be different than the rules for estimating when you use, for example, inches and feet. So I would kind of shy away from measuring stuff in inches and feet, because the rules for estimating the estimating digit is different than the rules for estimating when we're using the metric centimeters and millimeters. So if you had to measure something and you need to do the significant figures, it's best to stick with the metric system. And so here we have a ruler. We want to measure the length of this piece of metal. And so what we know for sure is our certain digits. You see that we start with centimeters, and between each large tick mark of centimeters, there are 10 tick marks between them. So this means that the certain digits should go to the tenths place. So we know for certain, if we write our certain digits, we know for certain it's 3. point, and we know for certain it's 3.2. Now that we've done our certain digits, now we got to do our estimated digit. And our estimated digit is just what you, with your own observation, what you think it is. So I'm going to go with a 6. So now when we write our measurement, we have to combine the certain digit and the estimated digit. So I'll say measurement, and it's going to be 3.26. So the estimated digit is to the right of the last certain digit. So this would be 3.26 centimeters. Now if you put 3.27 centimeters or 3.28, commonly people put 3.25 because their argument is that you can't really distinguish between 0.01. So you kind of, you know, it's generally it's either a 5 or a 0. If it's close to the 2, we would say 3.20. If it's close in the middle-ish, they say 3.25. But regardless, it has to have 3 significant figures. So if you put 6, 7, 4, 5, you know, that's no problem. So that would be the measurement of this piece of fabric or metal. Now when we get to something that is for volume, we have a graduated cylinder. When you add liquid to a graduated cylinder, it forms what's called a meniscus. I think we touched on that in the other lecture. And you want to read the volume at the minimum of the meniscus. So the minimum would be, you know, right about here. And so again, we want to look at our certain digits. So our certain digits, if we look at the tick marks between 20 and 25, you know, we have 21, 22, 23, 24, 25. So the tick marks represent 1 milliliter. So our certain digits should go to the ones place. So what we know for certain is it's 20, 21. Now we need our estimated digit. So our estimated digit, based on your observation, you look at the graduated cylinder, you see, okay, what do I think it is? I think the estimated digit should be a 5. So now when we write our measurement, the estimated digit comes to the right of the placeholder to the right of the last certain digit. So this would be 21.5 and milliliters. So it would have 3 significant figures. Now, if you put 21.4 or 21.6, etc., there's no issue with that. The thing you have to remember is that this measurement has 3 significant figures. If you use a different type of glassware that has tick marks that go smaller, for example, a burette that has tick marks to the tenths of a milliliter, then you would get a more precise measurement of your volume. And so on. So I'm moving along now. Now we're going to get into unit conversions, converting between the standard system and the metric system. And as you can imagine, we have many different types of units depending on what system we're going to use. For example, we have kilometers, we have centimeters, we have nanometers. On the English side, we have feet, inches, yards, miles. So you see there's all these different types of units for different types of quantities. So there was a need to have a consistent set of units for the different quantities. And these are called SI units, which are a standard system of measurements for these quantities that all people recognize. Now, the SI unit doesn't mean it's its most commonly used unit. It's just a standard unit that people have agreed on for that particular quantity. And so there are 7 base units, which all other units for other quantities are derived from. So for example, for mass, the SI unit is kilogram. Now, just because the SI unit is kilogram, in the lab setting, we usually do measurements in grams. And a lot of these SI units are the metric system, but not all of them. And again, it's just the standard unit that they recognize for the different quantities. For length, it's meter, but in the lab, we usually measure in centimeters and millimeters. For time, it's second. Now for temperature, it's unique. I don't know if you've read up on the different types of temperature scales yet, but there are 3 types of temperature scales: Fahrenheit, Celsius, and Kelvin. So Fahrenheit is the standard English unit for temperature. Celsius is for the metric unit, and Kelvin is its own unit. Kelvin, what's unique about that is it's an absolute temperature. So what that means is that Kelvin cannot be negative. So the coldest anything in the universe can be is 0 Kelvin. And when you read up on these different temperature units, you'll see the equations they use to calculate between them. Now, Celsius is based on the physical properties of water. That's why 0 Celsius is the freezing point, melting point of ice water, whichever one you're talking about, and 100 degrees Celsius is the boiling point of water. But again, Fahrenheit and Celsius can be negative, but Kelvin can never be negative. So if you want to see how cold you can get, the coldest anything in the universe can be is 0 Kelvin. For electric current, we use the ampere. For amount of substance, we use mole, and we'll talk more about that, I believe, in a later chapter. And luminous intensity, we have the candela. So all other units are derived from these 7 base units. So what do we mean by other units? For example, if we look at volume, if you think of volume of a cube or like a rectangular prism, it's going to be length times width times height. So since the SI unit for length is meter, the SI unit for volume would be meter cubed. And now meter cubed, to give you an idea of how large it is 1,000 liters equals 1 meter cubed. To put that in perspective, that's like 500 2-liter bottles is 1 liter cubed. So it's not a very practical unit of measurement, especially in the lab, but it's the standard unit recognized for volume. Next, we have density. So density, as we'll learn a little bit later, is mass over volume. So the SI unit for mass is kilogram. The SI unit for volume is meter cubed. And that's where we get the SI unit kilogram per meter cubed. So we have this standard system of measurements that we recognize for the different quantities. Doesn't mean it's the most commonly used one. It's just the one that they recognize for scientific purposes. Now we're going to do some unit conversions. I thought I had a slide. Let me see. Oh, no. Nope. So when we're doing conversion factors between the standard and metric system, we need to have a list of conversion factors that we commonly use because we have to convert between the two. And so for length, some common ones are, for example, 1 meter is 39.37 inches. 1 inch is 2.54 centimeters. Now remember that every metric to English conversion factor that's not inch to centimeter is not exact. So only 1 inch is 2.54 centimeters is an exact, or excuse me, 1 inch to 2.54 centimeters is the only exact conversion factor. All other ones have a certain number of significant figures associated with it. Another conversion factor for length some people use is 1.607 kilometers equals 1 mile. And so these are what we need to know in order to go from the English or standard system to the metric system. Likewise with volume, for example, 1 liter is 1.06 quarts, or 1 gallon is 3.79 liters. So it's very good to remember at least one of these conversion factors between the for the different quantities. Now 1 centimeter cubed equals 1 milliliter. This is an exact conversion because they're both in the metric system. Another common one for volume is 1 quart equals 946 milliliters. For mass, the two most common are 1 kilogram is 2.2 pounds, and 1 pound is 454 grams. So when we're doing our conversions, we're going to be referring back to these in order to convert from English or standard to metric. So now I have some examples, and I kind of made these examples a little bit interesting with putting some information about TV shows in them. Maybe you can catch on what we're talking about. So the first one, we have Dustin walks 40.3 yards to visit the head Demogorgon in the upside down world. How many meters did he travel? So here what we're looking for is meters. That's what we want. What we're given is yards. What we know is that 1 meter is 30.28 feet. So in order to get from yards to meters, we have to go through feet. So what we're going to do is we're going to convert yards to feet, and then we can convert feet to meters because we know what the conversion factor of feet to meters is. So the only other conversion factor we need is that 3 feet equals 1 yard. So now we're going to set up our train track. And we're going to start with 40.3 yards. So since we're starting with yards on the left, in our conversion factor of feet and yards, yards is going to go on the bottom, and feet is going to go up top. Now that we have feet up top now, we need to convert from feet to meters. And since feet is on top in our conversion factor, feet will be on the bottom, and meter on top. So now you'll notice that everything cancels but the meter. So again, everything on top we multiply, everything on the bottom we divide. And so Mr. Calculator gives me, let me double check Mr. Calculator. Yep, gives me 3.9927345 meters. So that's what the calculator gives me. But since this is metric to standard conversions, we have to look at the significant figures and choose the number of the original numbers or conversion factors in our operation that had the fewest, so that we know what to round the answer to. So 40.3 has 3 conversion factors. 30.28 has 4. 3 feet equals 1 yard. Since they're both in the standard system, this is exact. So we don't have to worry about that one. So the one with the fewest is 3. So we go 1, 2, 3. After the 9 is a 2. So we're just going to drop all this. And our answer is 3.99 meters. So that's how far Dustin walked to meet the Demogorgon. In the next example, we're now back in Middle Earth, and a Kreniki egg has a mass of 855 grams. So what is the weight of, or I should say, yeah, what is the weight of the egg in pounds? Not eggs, my bad. I thought I had a conversion. Maybe not. So we need a conversion factor in order to get from grams to pounds. So the one I'm going to use so in number one, since we're looking at multiplication and division, we have to look at the one with the fewest number of significant figures. Not to get confused with addition and subtraction, which is the least number of significant decimal places. So here we're just doing multiplication and division. So in number two, we need to look at, we need a metric to English conversion factor. So I'm going to do 1 kilogram equals 2.2 pounds. So what I'm going to do, we're looking for pounds and we have grams. So grams, from grams we're going to go to kilograms, and then from kilograms we're going to go to pounds. Now you could have used a different conversion factor, maybe you do it slightly differently, but we should come to the same point. Now we draw our train tracks. So again, we have our initial value, 855 grams. Now we're going to convert grams to kilograms. So based on previous lecture, we know that 1 kilogram is 1,000 grams. So since we're starting with grams, in our conversion factor in the middle train track, grams goes on the bottom. Excuse me. And kilogram goes on top. Now we're at kilograms, so next thing we want to do is go to pounds. And so in our conversion factor of kilograms to pounds, kilogram goes on the bottom, and pounds goes on top. And so you see here that the grams cancel and the kilograms cancel. So everything on top we multiply and we divide by everything on the bottom. And so we get 1.881 pounds. That's a big bird. That's a big egg. So now we got to round to the correct number of significant figures. So we see which number that we originally started with had the fewest. So 855 has 3 significant figures. Now we look at our conversion factors. 1 kilogram equals 2.2 pounds. This has 2 significant figures. And 1 kilogram is 1,000 grams is exact because it's in the same system of measurements. So we have to round this to 2 significant figures. So we go 1, 2. After the 8 is another 8, so that's greater than 5. So we're going to round the 8 up to 9. So it'd be 1.9 pounds. So the way we know to start where to put stuff on the train track is we start with what's given to us in the problem. It's 855 grams. And since we're starting with grams, we look at our process. We're going to go from grams to kilograms. So we got to use the conversion that has grams and kilograms in it, which is over here. The 1 kilogram equals 1,000 grams. So since we're starting with grams, in the next set of train tracks, grams goes on the bottom kilogram goes on top. So now we're at the middle part of our process. We want to go to pounds next. So in this conversion factor, 1 kilogram is 2.2 pounds. Since kilogram is already on top in the previous train track, in the new train track, it's going to be on the bottom, and then pounds goes on top. Because one has to be on top and one has to be on the bottom for the units to cancel out. And so that's how we know what order to put the conversion factors in. We write this process, and this process tells us the order to do it in. So now going back to the upside down world, traveling back from Middle Earth, where we have large birds. Dustin finds 3,500 pints of ale behind a tree in the upside down world. How many liters of ale did he find? So what we're looking for is liters, because that's what the problem wants. It wants to know how many liters of ale did he find. And so we're given that 1 gallon is 3.79 liters, and we're starting with pints. So somehow we have to get from pints to gallons, and we know that there are, in pints, we go to quarts, and from quarts we go to gallons, and once we get to gallons, we can get to liters. So in addition to the conversion factor given to us, we're also going to need to know how many pints in a quart, which is 2, and how many quarts in a gallon, which is 4. So 4 quarts make a gallon, 2 pints make a quart. So now we're ready to draw our train tracks. So again, we start with the initial number, 3,500 pints. Now, if we look at our process, we're going to go from pints to quarts. And so in our conversion factor of quarts and pints, pints goes on the bottom, and quarts go on top. In the next train track, we want to go from quarts to gallons. So since in the previous train track, quarts is on top, in our conversion factor of gallons and quarts, quarts would go on the bottom, and gallon goes on top. Now on the final train track, we want to go from gallons to liters. So in the previous train track, gallon is on top. So in our conversion factor of gallons and liters, gallon will go on the bottom, and liters will go on top. And so now you'll notice that everything cancels out but liters. So everything on top we multiply, we divide by everything on the bottom. And we get 1, 6, 5, 8. Let me just double check. Yep. So we get 1,658.125 liters. Now we have to look at the significant figures. So in our original number, we have 2 significant figures because there's no decimal point at the end. So only the 3 and the 5 are significant. Gallon to liters, that's standard to metric. So this is standard. This is metric. So we have to include the sig figs. So it's 3. Now quarts to pints and gallon to quarts, it's okay. It's let's go. They're in the same system of measurement. So we need to round our answer to 2 sig figs. So 1, 2. After the 6, it's 58125, which is greater than 5. So we're going to round up to 1700. So there's 1700 liters of ale behind the tree. In our next example, we go back down to Middle Earth. And here Frodo travels 65,600 Rangar, which is a unit of distance in Middle Earth from the Gulf of Linden to Mount Doom. And 1 Rangar is 2.9987 miles. How many kilometers did he travel if 1 mile is 1.607 kilometers? So in this problem, what we're looking for is kilometers. What we're given is Rangar, a unit of distance in Middle Earth. So what we're going to do is from Rangar, we can find miles, and from miles, we can find kilometers. And we already have all the conversion factors given to us. So now we can go and set up our train tracks. So we're going to start with our initial number, 65,600 Rangar. And it's an actual distance of measurement, measurement of length in Middle Earth. So now, since we're starting with Rangar, in our conversion factor of Rangar to miles, we're going to put Rangar on the bottom, and we're going to put miles on top.
Could you scroll up a little bit, please?
Next time, put it in the chat, please. I'll check it. I can't scroll up. Oh, let me try this. No, that didn't work. That was worse. Unfortunately, I can't scroll up. It's like that. So I'll take a pic of it as well. I think we can. No, we can't. Okay. So then we have miles. We got to go from miles to kilometers. So what we're going to do is, in our conversion factor, we're going to put miles on the bottom and kilometers on top. So now everything cancels but kilometers. So now we can multiply everything that's on top. And we get, let's see, 31. Oops. 31. So this is how many kilometers we get. Now we have to round to the correct number of significant figures. So our initial number had 3 significant figures because these 2 zeros are not significant. So because there's no decimal point. One Rangar equals 2.9987 miles. These are two different systems of measurements. So this has 5 significant figures. And 1 mile is 1.607 kilometers. Again, that's two different systems of measurement, so that has 4. So our answer should have 3 significant figures. So after the 6 is a 1. And so this should be 316,000 kilometers. So now these are more like, I want to say, dimensional now, like problem solving, than the ones on the previous slide. So here what we're doing is we're solving a word problem. We're on the last one. It was just mainly just converting from one unit to another. But here we want to actually do a word problem or problem solving. So here we have Bilbo has 24% of his, it should be 24% fat per his body weight. Let me write that in. So Bilbo has 24% fat per his body weight. If Bilbo weighs 78.6 pounds, how many kilograms of body fat does Bilbo have? And we give you the conversion that 1 kilogram is 2.205 pounds. So we have Bilbo, he's gone to the doctor. They told him, hey, you got 24% fat per his body weight. If he weighs 78.6 pounds, how many kilograms of body fat does Bilbo have? Now, there's many different ways you can approach a problem like this. So if I do it this one way, there could be other ways to do it. So if you do it a different way, we end up with the same answer. There's no problem. So what we're looking for is kilograms of body fat. So that's what we're looking for. What we know is his weight in pounds. So the obvious direction to go is to take his weight in pounds and convert it into kilograms. And then we know that 24% of his body weight is fat. So once we know it in kilograms, we can find the, so this is going to be, I guess you call it kilograms of body weight. And then we're going to go to kilograms of fat. So again, we're starting with he weighs 78.6 pounds. We're going to convert those pounds into kilograms so we can get his weight in kilograms. And then once we know his weight in kilograms, we know that 24% of that is fat. So then we can multiply that or take 24% of that and we'll determine the number of kilograms of fat Bilbo has. So the conversion factors we need are all given to us. So 24% of his body weight is fat. He weighs 78.6 pounds. We want to know how many kilograms of body fat does Bilbo have. So our plan of action is to take the pounds, convert it into kilograms to get his body weight in kilograms, and then we're going to take 24% of that to get kilograms of fat. So we start with 78.6 pounds. Since we're starting with pounds in our conversion factor in the next train track, pounds goes on the bottom. Kilogram goes on top. And we get 35.64 626 kilograms. And this is kilograms of, I guess, kilograms of bilbo. This is how much bilbo weighs in kilograms. Now, in order to find the kilograms of fat, we got to take 24% of that. And remember, when you see a percent is equal to the part divided by the whole times 100. So in order to use this, we're going to have to take the percent and divide it by 100. So when you multiply this, you're not multiplying it by 24, you're multiplying it by 0.24, or 24 divided by 100. So now what we're going to do is we're going to take the mass of bilbo, yeah, so the percent is the part over the whole, so 24%. If we want to find the part over the whole, we just take 24 over 100 times the mass of bilbo. So you can't just use 24%, you have to use 24 over 100. Let me write that better.
When you do this part,
If you could, when we're recording, not to ask questions, and we're going to pause and you can come back, because then I have to go back and remove it from the video. So, or just ask in the chat box. That's better. So you can do 24 over 100, or you could do just 0.24, because 24 divided by 100 is 0.24. And so we'll get what 24% of this number is. So we get that many kilograms of fat. No, so when you do the multiplying by 24%, you have to use the whole number. It's at the very end that we take the number of significant figures. So now we're at the end. We got to look and see which number had the fewest significant figures. So 24% had 2 significant figures. The 78.6 pounds had 3. And the kilograms to pounds had 4. And so if you would have rounded at this stage the 35.64626, you know, here we're okay because we have to round to 2 sig figs. But if, for example, you had a round to say 6 sig figs, then you would have been off. So as long as you look at your initial numbers and you round to a few more sig figs than the number of sig figs for the number of the one with the most sig figs, you'll be okay. So since the number here is 4, which is the most, as long as you round to more than 4 sig figs in each step, it won't be a problem. But you know, don't round too much. So if you would have rounded to say 35.6, that might have been too much rounding in this part. So it's always best to wait till the end to round. So we need 2 sig figs. So we go 1, 2, after the 5 is 55102. And so this is 8.6. 8.6 kilograms. And at the end, I'll pause if you have any questions about that. So now moving on, we're looking at Irene prepares an elf stew containing cabbage, and the recipe calls for 5 heads of cabbage. Each head of cabbage has a mass of 357 grams. At the local elf market, cabbage costs 12 silver cast star coins per pound. How much will the cabbage cost Irene? So we have an elf here preparing a stew. The recipe calls for 5 heads of cabbage. Each cabbage has roughly 357 grams. A cabbage costs 12 casters per pound. So how much cabbage will the cabbage cost Irene? And we get that 1 kilogram is 2.205 pounds. So what we're looking for is the cost. So how much does this cost? And again, there are several different ways to approach this problem. So the way I'm going to approach is I'm going to take the number of cabbage, and from that I'm going to get the total mass of cabbage. Because if I know the mass of 1 cabbage is 357 grams and I have 5 heads of cabbage, I can determine the total mass of all the 5 heads of cabbage. And this is going to be in grams. Now that we have it in grams, we need to get to pounds to determine how many coins it's going to cost. And so we have 1 kilogram is 2.205 pounds. So we need to convert grams into kilograms of the mass of cabbage. Once we get kilograms, we can get pounds, and then once we know the pounds, we can get the number of coins. So this is the way we're going to do it. So let me just go through it one more time. So this recipe calls for 5 heads of cabbage. Each head of cabbage has a mass of 357 grams. At the local market, it costs 12 coins per pound of cabbage. So how much will the cabbage cost Irene? And it gives us that 1 kilogram is 2.205 pounds. So what we're going to do is we're going to take the 5 heads of cabbage, determine the total mass of the 5 heads of cabbage. That's going to be in grams. And then we're going to convert that to kilograms, then the pounds, and then we can know the number of coins. So what we know is that 1 pound equals 12 coins. And that's given to us in the problem. It says 12 silver caster coins per pound. And so that's an additional conversion factor that we'll need. So now we're ready for our train tracks. Total mass of cabbage, kilograms, pounds, coins. One conversion factor I forgot is grams to kilograms. So 1 kilogram, 1,000 grams. So now we're ready to start doing our calculations. So we start with 5 cabbage. Now we know that 1 cabbage is 357 grams. So if we write that as a conversion factor, it would look like this: 1 cabbage, 357 grams. So again, the 1 cabbage goes on the bottom. The 357 grams goes on top. Now we're at the gram. So we're at stage 2 of our process. The next set of train tracks, we're going to go from grams to kilograms. So in our conversion factor of grams to kilograms, grams goes at the bottom and kilograms goes on top. Now that we have kilograms, we're at step 3. So the next step is to convert it to pounds. So that's our next set of train tracks, what we're going to do. So we know that 1 kilogram is 2.205 pounds. And so we put kilogram on the bottom, 2.205 pounds on top. And then lastly, we're at the last step. We know that 1 pound is 12 coins. So 1 pound goes on the bottom, 12 coins on top. So now we're ready to multiply everything on top and divide by everything on the bottom. So luckily there's only one thing on the bottom, so it makes it a little bit easier. And so we get 47.2311 coins. Let me double check. Yeah, but we're not finished. So now the thing is we're calculating number of coins, and so a coin is something you can count. So we can't count. We can only count whole coins. So we're going to have to round this to a whole number because you can't count 47.23 coins. A coin is something that you can count. So we're going to round this to a whole number, and the closest whole number is 47. So it would cost 47 coins to purchase the 5 cabbages. So again, coin is something you can count. It has to be a whole coin. We don't have half coins. So that's why we round it to the nearest whole number. Now to the last example. Here we have Lizzie Saltzman. She's a witch. Places a containment spell on Landon, which lasts for 75 seconds. If Raph runs at a speed of 18 kilometers per second, how many miles will he travel in that time? So we have Lizzie puts a spell. The spell lasts for 75 seconds. If Raph, who's actually a werewolf, runs at a speed of 18 kilometers per second, how many miles will he travel in that time? So again, what we're looking for is miles. And so now we got to come up with a way we're going to solve for this. So we're given time. So we're starting that the time is 75 seconds. So how far can he travel in 75 seconds? So from time, if we know the speed, we can determine the kilometers that he's traveled, because we know that for every second he runs, he covers 18 kilometers. So again, since it's 18 kilometers per second, what that means is if we write that as a conversion factor, 1 second equals 18 kilometers. So that means for every second that he runs, he covers 18 kilometers. So now from the time we can get kilometers, and then from our conversion factor, we can get miles. And this will tell us how many miles Raph had run. So again, the 18 kilometers per second means that for every second that he runs, he covers 18 kilometers. So now we're ready to set up our train track. And we're starting with 75 seconds. So in the first set of train tracks, we're going to go from time to kilometers, and that conversion factor is 1 second equals 18 kilometers. So the second goes on the bottom, and the 18 kilometers goes on top. So that's the first step. The second step, we go from kilometers to miles. So in the next set of train tracks, kilometer goes on the bottom, and mile goes on top. And again, you see that everything cancels but mile. So now we multiply everything on the top, we divide by what's on the bottom. And so the answer we get is 840.0746 miles. Let me double check. Yep. So 840 miles, that's about from here maybe to about Memphis, Tennessee. It's pretty fast. Or from here to El Paso. No, El Paso's 500. It's like crossing the state of Texas. So now we need to round to the correct significant figures. So again, 75 has 2 significant figures. 18 has 2 significant figures. And our conversion factor has 4. So we need to round to 2 significant figures. So 1, 2, after the 4 is a 0. So we just rounded to 840 miles. So Ralph traveled 840 miles in 75 seconds. And so when we're talking about unit conversions, we mentioned density at the beginning, but density is usually a property that people investigate a little bit more. It's a physical property. So physical property means it doesn't change the identity of the substance. And so you can actually define, or you can actually determine what a substance is by measuring its density, because all substances have a different density associated with them. And as we mentioned earlier, the SI unit for density is kilograms per meter cubed, and it's the ratio between the mass of a substance and its volume. Some common units of density that we use are grams per milliliter for solids and liquids. Like, for example, commonly water density is usually 1.0 or 1.0 grams per milliliter. But for gases, which are a lot less dense than solids and liquids, for gases we usually use grams per liter. So these are the common units that we use when describing densities. And again, every substance, if it's an element, if it's a compound, they all have their own unique densities associated with them. So in some labs, and actually what we usually do in lab when we're meeting in labs, is that we do an experiment where we determine the density of a metal by measuring its density. And so typically with the physical states, the solid is the most dense form of the physical state, and the gas is the least. However, there are some exceptions, such as water, where the solid is less dense than the liquid. And that's why the ice floats in the water when you put a couple of cubes of ice in a glass of water. Now, one thing you got to remember is that if you increase the mass of your substance at a constant volume, your density is going to increase. Whereas if you increase the volume at a constant mass, your density decreases. And so how do we find density? There are a bunch of different ways you can determine density. One way, and I think this is usually done in labs, is you take the mass of a substance, you determine its volume, and the slope of the line will give you its density. So again, mass on the y-axis, volume on the x-axis. So for example, if you go into the lab and you measure 5 grams of water, or excuse me, 5 milliliters of water, and you measure its mass, and then you measure 10 milliliters of water and measure its mass, and do this for 2 more times, and you plot it, when you take the slope of that line, you would determine the density of water. So the more steep the line is, the greater your density is of that substance. And this is a very common way to calculate the density of a substance, is by taking the volume of that substance at, like, say, for example, 5, 10, 15, 20 milliliters, and measuring the mass of that substance, and then plotting that or graphing that, and you'll determine what the density is. Also, we use density qualitatively to determine if something is less dense or more dense than another substance. So if we look at this picture on the right-hand side, we see water, and above water we have oil, and below water we have syrup. Now, as I said earlier, we know that water has a density close to 1 gram per milliliter. Now, just to let you know, density does change with temperature, but if we're at room temperature, normally we use the 1 gram per milliliter to signify the density of water. So when you have a substance that sits on top of water, this tells you that the substance density is less than water. So oil here would have a density less than 1, because oil sits on top of the water. So if something sits on top of the water, that tells you its density is less than that of water. Now, if you put something in water and it kind of suspended in the water, neither going to the top or the bottom, that tells you that that object or that substance has a density very close to the density of water. Now, if we look at syrup, syrup is below the water. So when something, so example, if we know that water has a density of 1, when we look at syrup, which is below water, that's going to have a density greater than 1. Because if something is more dense, it's going to sink or settle to the bottom. If something is less dense, it's going to go to the top. So now if we want to calculate the density of a substance, say we have 43.7 milliliters of ethanol. It has a mass of 37.32. What is its density? And so again, density is mass over volume, and we get 0.789 grams per milliliter. We can also do other calculations with density. So let's say we have 116 grams of ethanol. What volume of liquid would you use? And so therefore, we can rearrange the equation to solve for volume. So what you would have to do is, if you want to solve for volume, you move volume to the left and you bring density down on the right. And you get volume is equal to the mass divided by density. And so you would need 147 milliliters of ethanol to have a mass of 116 grams. Likewise, if you wanted to determine the mass and you're given density and volume, mass equals volume times density. So let's look at some problems involving density. So we have silver. It has a density of 10.3 grams per milliliter. Just to let you know, if you see grams per milliliter or gram per centimeter cube, it's the exact same thing. And so this cube of silver occupies 27 milliliters. How many ounces of pure silver are present? And it gives us that 1 pound is 454 grams. So the problem is asking us how many ounces are present. And we're given the density and the volume, and we're asked to find how much of it is present. So since we're given the volume, and the volume is in milliliters, we can take the volume that's in milliliters and we can find the mass in grams by using the density. So what we're going to do is we're going to use the density to determine the mass. And so once we get the mass in grams, we can find kilograms, the mass in kilograms, and then we can find the mass in pounds, or weight in pounds. And so that's what we're going to do. We're going to first take the volume and the density to determine the mass in grams. Oh, we got one more step, and then we got to find the mass. Oh, hold on. Let's back up a little bit. Yeah. So I made a mistake. Since it's 1 pound is 454 grams, we can find the mass in grams, and then we can go directly to mass in pounds, or we can go directly to pounds because we know how many grams are in a pound. And then we can go to ounces. I was thinking about the previous conversion factor. So now we need any other conversion factors. We need to know how many ounces in a pound. That's 16. So now we can set up our train tracks. Volume. Now you can take the density and write it as a conversion factor. So if we take 10.3 grams per milliliter, we can rewrite it as 10.3 grams equals 1 milliliter. That'll help us in doing the train tracks. So we're going to start with 27 milliliters. Now we need to convert the milliliters to grams. So that's where we're going to use this 10.3 grams equals 1 milliliter. So we're going to put the milliliter on the bottom and the grams on top. So now we've done the first step. We've gone from volume to grams. Now we need to go from grams to pounds in the next set of train tracks. So since we're starting with grams to the left, we're going to put grams on the bottom, and we're going to put pounds on top. Now we've completed the third step, or the second step in our process. The last step is to convert to ounces. So we're going to use this 16 ounces as 1 pound for the last train track. And so here, since we're starting with pounds on the left, we're going to put 1 pound on the bottom, 16 ounces on top. And everything cancels but the unit we want. So again, you're going to multiply everything on top, divide by what's on the bottom. And so I get in the calculator 9.8008 or 009 ounces. But we're not finished. We need to look through all the numbers originally given to us, determine the number of significant figures, and see which one has the fewest significant figures. So 10.3 has 3 significant figures. 27 has 2. 1 pound equals 454 grams has 3. And then 16 ounces is 1 pound. That's an exact conversion because it's in the same system of measurement. So we got to round to 2 sig figs. So we go 1, 2, we have 9.8. And after the 8 is a 0. So we just drop everything and we have 9.8 ounces. Now there are different ways to measure volume when you're dealing with density. One way is what we call volume by calculation. So you can measure if you have a cube, for example, you can measure the length, the width, and the height, and you can determine the volume of a cube. Or if you have a volume of any kind of regular shaped object, like a cylinder or a sphere, it's very straightforward on how to determine the volume. You just measure, and then you get the volume. However, if we have an irregular shaped object, like a piece of rock or a lump of copper, we have to use a different type of process to measure the volume. And that process is called water displacement method. So in the next problem, when we look, it says lead has a density of 11.3 grams. And then a student drops a piece of lead into the graduated cylinder. The cylinder initially had a volume of 25.5 milliliters. When he drops the lead in, the volume increases to 46.3. What's the mass of lead that was added? So when we have water displacement or volume displacement method, we have an original volume. We add our object. The volume of liquid increases. The difference between the two is the volume of the object. So let me draw a graduated cylinder, or a very rudimentary graduated cylinder. So initially, we have 25.5 milliliters. Then we drop a rock in it, which is our final, and the volume increases to 46.3. Again, this is after we've dropped the rock or a piece of lead into the graduated cylinder. So before we added any lead, it was 25.5. After we've dropped a piece of lead in it, it raised to 46.3. So the volume of lead is going to be 46.3 minus 25.5. And we get 20.8 milliliters. And so that's how we found the volume of the lead. Now we're looking for the mass of the lead, and as we know from density, mass equals volume times density. And we can write density as a conversion factor. There are 11.3 grams equal to 1 milliliter. So now we're ready to write our train track. So we're going to start with the volume of the lead, which is 20.8 milliliters. And now from our conversion factor, 1 milliliter goes on the bottom. And the gram goes on top. And so this will tell us the grams of lead in that piece of lead. It's 235. So this is what the calculator tells us. Now we need to go back and look at all the original numbers. So the density has 3 significant figures. Initial volume has 3. The final volume has 3. So our answer should have 3. So after the 5 is a 0. So this becomes 235 grams. Now moving on to number 3. We have a graduated cylinder, has an initial volume of 15.5 milliliters. We put a 45.5 gram piece of bone to the graduated cylinder. If the bone has a density of 1.8 milliliters, what's the final volume of the graduated cylinder? So here again, it's good if we draw a little picture. So we have a graduated cylinder. And this is very similar to what you would do in the lab, would be experiments like this. And initially we have 15.5 milliliters. Now after we add the piece of bone, we know that the volume of water is going to increase, but we don't know what it is, and that's what we want to find out. So again, this is after we've added the piece of bone. So this is our final. And so what we have to remember is that for water displacement, the volume of the object equals the final volume minus the initial volume. So the initial volume we have, it was given to us in the problem. It's the final volume that we're looking for. So in order to find the final volume, if we rewrite this, we need to know the final volume is equal to the volume of the object plus the initial volume. So if we know the initial volume and we know the volume of the object, we can determine the final volume of the graduated cylinder. But currently, we do not know what the volume of the object is. So this is something we need to find out based on the other information. And so what we know is we know the mass of the object. It's 45.5 grams. And we know the density of the object, 1.80 grams per milliliter. And so if we know the mass and we know the density of the object, we can determine the volume, because volume equals mass divided by density. And so we can rewrite this as a conversion factor, 1.80 grams equals 1 milliliter. So now we can do our train track. We start with 45.5 grams. Now since we're starting with grams, in the bottom goes the grams, and in the top goes the milliliters. So we get 25.2778. And so we can go ahead and round this to 3 significant figures because we're going to use it in another operation. Or we can keep it and then we can do it at the end. We'll do it at the end. So now we have 25.2778 milliliters, and our initial volume is 15.5. So now we know the volume of object. We can determine the final volume. And so we get 40.778. And that would be the final volume of the graduated cylinder. But we're not finished, because remember the addition and subtraction. What do we look at? We look at the number with the least number of significant decimal places. So our first number that we took from the calculation, you know, it's 4 decimal, all the way to the 10 thousandths. Now, if we would have rounded there, we would have just got 25.3. But since we didn't round, because we shouldn't round to the end, we get 25.2778. Now the other number is known to the tenths place. So since it's known to the tenths place, we gotta round this to the tenths place. So we have 40.7. After the 7 is a 7, so our final answer, let me put it over here, V final is 40.8 milliliters. Now notice if we would have rounded the 3 significant figures and got 25.3, 25.3 plus 15.5 also gives us 40.8. But it's better to save the rounding to the end.